Hi everyone, I'm glad to present this paper. I'm Yikang, and the paper I present is an impressive zero-knowledge set accumulator, which was published in EuroSP 2017 by Zhang Yupeng from University of Maryland. So let's quickly dive into the paper now. So the paper consider problem settings that someone own the data and want to outsource the data storage to a server. Then other client can issue queries on the data and want to verify the correctness of the query result provided by the server. So we also want the data owner and other people can also incrementally update the data. So basically, the problem setting can be formalized as a set accumulator. So there is a more formal definition here, assuming that a dynamic connection of an M set S1 to the SM is remotely stored and trusted server, and we wish to publicly verify primitive queries on this set, such as intersection, union, set difference. So there is a concrete example, and we want to develop some technique that allow any client to cryptographically check the correctness of the intersection result returned by the server. So here is the paper, what paper proposed, impressive set accumulators. So with three nice properties. The first is expressively, which means our set accumulator support various operations like intersection, union, set difference, and some count, min, max, range, and also listing of these operations. And the second property is efficiency, which means proof size and verification complexity both does not depend on the original set. That will be bad. And the big goal of proof size is the absolute query size Q. And the verification complexity is absolute query size plus absolute result size. And the third one is we want the scheme would be zero knowledge. And we will see how the paper extend expressive set accumulator to be a zero knowledge one. So before we show the behind intuition of this ESA scheme, let's simply go through necessary background to understand the paper. So the first is we use the K to denote the security parameter, and PPT denote probabilistic polynomial time, and we use A for a set and a bracket X and a bracket XY for characteristic polynomials of a set A. And we also use such symbol to denote running algorithm C and D together, where C output C and D output D. So that's the preliminaries. And so that the first thing need to be defined is a group. A group is a set of elements with our operation star that satisfy four properties: closure, associativity, and identity and inverse. So we use an example to go through this. Integer set with addition is a group. Obviously, any integer add to another integer is still integer, so that it satisfies closure. And also other three properties satisfies. So that's the group. So given the introduction of a group, then for every group there exists a generator, which is an element G that generate all elements in the group by taking all power of G. So let's still take an example. We have a multiplicative group modular set at the prime number 7. We can try different elements in this group by taking all the power of it. So for example, 2 to the 1, 2 to the 2, 2 to the 3, and 2 to the 6. But we can see that it cannot generate all elements in the group, right? So, but however, 3 can. So 3 is the generator of this group. Remember, the generator is not only one in some groups. Then this is the bilinear parents. So as known, with the definition of generator, we have a well-known problem called discrete logarithm problem. Given y, it is computationally hard to find x such that g to the power of x equals y. So, and also Diffie-Hellman problem. So, but bilinear pairs give the ability to compute g to the xy, given g to the x and g to the y, without knowing x and y. So the rule for the pairing operation is that it takes two elements in the base group as input, and sorry, and after pairing, it gives you an element in the target group, which equals to EPQ to the power of AB, and for all PQ. So let's still see this from an example. And given g to the x, g to the y, and after pairing, the pairing of these two elements equals to the EGG to the power of xy. And by a similar rule, this also equals to the pairing between g to the power of xy and g itself. So basically, this bilinear pairing gives us a tool to verify the product relationship in the explosion of the computation, but no in the concrete number values. Know that using pairing, we still cannot break the computational Diffie-Hellman assumption. We cannot compute the g to the xy directly. So this is called Q-strong bilinear Diffie-Hellman assumption. So basically, it's same as the Diffie-Hellman assumption or also the discrete logarithm problems. So this can be recklessly reduced to Diffie-Hellman assumption. So this is one assumption we use in this paper. And now we show the behind intuition of the ESA. So we take intersection as example because the other cell operation can be handled like the intersection operation. So we have two sets, A and B, and A set have three elements, 1, 2, 3, and B has three elements, 1, 3, 5. And our accumulator constructed by this equation and this equation. So the digest of A set is that g to the power of s plus s to s squared plus s cubed. And also the B set, the digest of B set, we do this. Just input every element into the equation. So SR are uniform secret point, private key. Later you will see. And so the product of these two exploded give this. So s plus s squared plus s cubed times rsq to the -1 and plus r to the 3 times sq minus 1 and also plus r to the 5 and s to the q minus 5. And after some computation, we will probably see that only when some element I is in the section of both sets, like the 1 and 3. So remember, we have 1 and 3 in the section result of these two sets. So the term r to the power of I times s to the power of q will be the result. So this a very good property and a true insight of this ESA construction. And know that QSR is the rest of the bivariate polynomial in the equation. So to compute the intersection, the server will send the intersection result. I will prove g to the power of QSR. Then the client can check the relation in the explosion using bilinear pairings. So other set operations can be reduced to the intersection. So we will not explain it. So then then for the single set operations, and we can simply compute the sum count when s is equal to 1. And for sum of the element of A is also when s equal to 1, but compute the formal derivative of AS. So we know that the polynomial in the explorer of digest as a bracket S. So then we can use the formal derivative to get the sum. And also the min and max operations, we find the lowest degree term and the highest degree term in the A bracket S. Range can be reduced to max min operations. So that's the behind intuition. So let me describe the whole process of our ESA again in general. So the first step is run by the data owner, and on input the security parameter and the universe U, the output secret key SK and a public key PK. So this is run by the owner. And the second algorithm is also run by the owner, and we will input the set A and the secret key SK, and in compute the digest DA of A. And in our conjunction, the digest can also be computed using PK only. So then the third algorithm is run by the client or input a digest DA and update and public key PK. You output the new digest DA prime of the updated set A prime. And the last is to query, and this is run by the server. So once the server receive a query queue, set A1 to the AL and the public key PK, we will return the result R and also the proof PyQ. And the final step is run by the client to verify the proof, to check the correctness of the proof. And so you will receive digest DA1 to the DAL of the set A1 to AL and proof PyQ, and also the corresponding query queue, and also the answer R and the public key PK. And you output either accept or reject. So that's the whole process. And let me show more details. So the first one is to set up. So the construction is same as the behind intuition we explained before. So we use this equation to set up the accumulator of A, also which means the digest of A set, and also for we also need to define the polynomial AXY and introduce another accumulator value as this. So this is like the behind intuition sample of the B set, right? So the last step is to change key. So we choose S, R, alpha, beta, gamma, epsilon as private key randomly from the domain. And we will set up a bilinear pairing as PUB pub. So our public key will contain these 5 components. And then we will need to compute the digest. So we set the digest as a vector of 4 group elements, and AS, ASR, and AR and IRS. So AS, ARS are used for set operations and functions, and we will see later. And AR and ASR are used for supporting nested queries. Then it comes to the update operation. And if update is an insertion of element W into set A. Then we update the group element contained DA prime as this for. So we will update the digest again as AS prime and AS R prime and AR prime and ARS prime. So deletion are done similarly by dividing. So now we have do the query, and here we only take the set intersection as an example, and as we read before. So we compute the polynomial QXY such that it satisfies this equation, and also we need to compute the ALY such that IY equals ALY times Y. And we need to compute these four values. We will output the intersection result as the result R here to return, and also the prime, the proof. So the proof will be IR this one, and IR beta, and QSR this one, and QSR epsilon, and also the ALR this one. So then finally, the client will need to accept, we need to accept if and only if using bilinear pairs to compute this equation. So more concretely, we will compute, we will accept it only if and only if this phi equation. So that's it. That's our set intersection. And for other set operations, can trivially use the intersection accumulator value to compute. And our current ESA only guarantees that a malicious server cannot return an incorrect answer to pass the verification. However, the client may learn extra information about the set through the proof, right? Here, the proof may leak many information here. So we need to extend the ESA to be a zero knowledge impressive accumulator, which means ZK-ESA. And it guarantees that even an malicious client cannot learn anything about the set beyond what is queried. So we only need to add the Surrey information for this set to hide the information of the set. And then the malicious client cannot distinguish whether he's interacting with the algorithm of the scheme or with the simulator that really exists but have no access to the set. Let me explain it more. And here we show two experiments that involve a challenge and an adversary and a simulator. And basically, we don't want any client distinguish the game between these two experiments. The first one is view one. So view one means that we use our ZK ESA, and the second one is the simulator. The simulator have no access to the set, and then it also will output the return the proof, and then the adversary cannot distinguish whether it's interacting with a simulator or view one. So that's the perfect zero knowledge ZK ESA. And so let me explain the construction in ZK ESA. So the construction is like this. Same as before, we set up private key and public key, but this time we add a randomizer T on the explosion of each element in the original ESA. As you see, we have more T private key, and then we added in all the explosion of each element compared to the original ESA. And so you compute the accumulated digest of set like this. And here we also add a more randomizer. So we have we need to randomly select R1, R2, R3, R4, and from the universe domain. We will send R1, R2, R4, R3, R4 as the auxiliary information to hide the set information. And so this will also be sent to the prover. And then we use min, max, R1, R2, R3, R4 for set A, and min prime, max prime, R5, R6, R7, RA for set B. And we will compute the accumulated digest of set like this. And like the intuition we explained at first, the product computation here, we only care about the term S to the power of Q. So we send the rest polynomial as the proof, like Q1. Q1 is equal to the G to the power of Q SRT R1 IA, and also give Q2. We have more epsilon times the Q SRT R1 IA, and return the result I. So the iteration is same here. And so that's it. And other steps are similar. And finally, client can verify using the bilinear pairing. And the original paper proved the soundness of this zero knowledge ESA. But we will not go into the detail of this today. And so if you are interested, you can read the original paper. And let me prove the last one, zero knowledge. So why an adversary cannot distinguish between these two experiments. So at first, step 1 and step 2 are always indistinguishable because they are same. And for the step 3 to the step 4, we need to know that R1 and RA are randomly chosen and are randomly selected. So adversary will not have any information of this, will not have access to these two numbers. So he cannot distinguish the step 3 and also the step 4. So in conclusion, these two cases are indistinguishable to any PPT adversary. So that's all for the JK ESA. And so what is the application of such scheme? So the first one will be keyword search. For example, we store file IDs of all the documents by having a common term in the dictionary. We group them into a set indexed by this term. So we can use a keyword search to query for some terms, word 1 and word 2. And then we hope it returns all the documents that contain both these two terms. And this can be modeled as an intersection of the two sets indexed by word 1 and word 2. So we can directly use JK ESA here. And also the second application would be SQL database queries. SQL queries can also obviously model as set operation like select or other difference join operations. So based on the JK ESA, we can build a verifiable database here. So let's come to the evaluation part. And to evaluation the ESA, the paper first evaluate the number of CPU cycles for the operation used in the ESA. There are 2 operations only used. one is multiplication, and another one is the pairing, the bilinear pairing. So a multiplication of the two elements in the group takes around 2,500 CPU cycles, and the pairing takes 1.4 million CPU cycles. And so the paper used the number of CPU cycles to estimate the running time to compare with ARM-based one. The ARM-based one is Slugs, which is published in the 2014 Using Security. So these CPU cycles correspond to the same machine in this paper is like 0.6 microsecond, and the parent is like 0.3 microsecond. So yeah, I'm very curious about why the CPU cycles is smaller than the pairing, but it takes longer time when they compute this this estimation running time in the paper. Yeah, this is the one strange point. And as the result, they compare the result, they see, as you see, when the set size is not that big, like under 10,000 elements, ESA is faster in all aspects in their result. And for larger set, when the set size reach 5 million, ESA proof time start to be slower, and the verification time is still faster than Slugs, as you see. So, and also the overhead of the proof size only 1.9 times than the Slugs. So yeah, let's say for larger set, Slugs are always better. But for reasonable set, ESA has an advantage in storage and time. So that's what the paper think the ESA's advantage is. And so as a summary, although the Slug has better proof time, proof size theoretically, but in practice, the author in this paper think they are more efficient in practice, especially when the set size is not that big, like 10,000 elements. So that's all for this paper, and hope you enjoy my presentation. And thank you very much.